back down the carbon-carbon pi bond electrons back over onto the alpha carbon. Imagine we're putting that lone pair back, and then we're using it. And I'm moving this R prime group down. I'm doing a bond rotation to get this out of my way. Then we're using that lone pair on carbon to attack the carbonyl carbon of our whatever that carbonyl compound is, pushing those CO pi electrons up onto oxygen to create the usual tetrahedral intermediate. We've added an enolate anion nucleophile to our carbonyl compound in this addition, this nucleophilic addition. And what happens next depends on the identity of X. It depends on whether we have a leaving group here or not, whether we're using an acid derivative or an aldehyde or ketone. So, scenario 1, X is a leaving group. So we're working on an acid derivative. What are the two key mechanistic steps in the reaction of any acid derivative with a nucleophile? What follows the addition? Elimination. So what happens is that our leaving group is subsequently eliminated. We reform the original carbonyl group that was present in the acid derivative. We kick out our leaving group X minus. That could be an alk oxide, that could be chloride. Again, depending on whether we're using an ester or an acid chloride. In either case, our product will be a so-called beta dicarbonyl compound, a 1,3 dicarbonyl compound. So reacting an enolate anion with an acid derivative will give a beta dicarbonyl compound through this addition elimination process, which is again no different from what you've seen before for carboxylic acid derivatives reacting with different nucleophiles, oxygen nucleophiles, nitrogen nucleophiles, carbon nucleophiles, including organometallic reagents. We see the addition elimination process play out in reduction mechanisms. So we're just plugging in a different nucleophile. Now, what if X is not a leaving group? Then there's nothing there to eliminate. In that scenario, what are the options? There's really only one thing that can happen under the right conditions, and that's a protonation of your tetrahedral intermediate. And if your solvent is protic, that can happen right away. And if it's not, there might be an acidic workup. We have to add a proton source for this to happen. But however we go about it, whatever the specific reaction conditions are, protonation of our tetrahedral intermediate will leave us with this hydroxyl group. Protonation gives this beta hydroxy carbonyl compound. Protonation of the tetrahedral intermediate gives this beta hydroxy carbonyl compound. And this can be the end of it if we want it to be. But oftentimes we don't want the reaction to end here. Oftentimes we want to dehydrate these beta hydroxy carbonyl compounds. We want to eliminate water. And sometimes that requires a little bit of heat, depending on the substrate. Some of them dehydrate very readily all by themselves without any input from us at room temperature. And what happens is that we dehydrate between the alpha position of the original carbonyl and the carbon bearing the hydroxyl group, like so. So we're taking this alpha hydrogen and that hydroxyl group, dehydration between the alpha and beta positions of the carbonyl group gives this alpha beta unsaturated carbonyl compound in this reaction. Product after dehydration is an alpha beta unsaturated carbonyl compound. So really this is in part, not in its entirety, but in part a reminder of how aldehydes and ketones and acid derivatives react with nucleophiles, right? Just a different nucleophile. Before we move on from here, I have a question, which is, when did Pete usually end class? Did he end it at 9:15 or earlier? 9:15. Okay, so you're used to 9:15. I'm asking because that gives us a little bit of breathing room. If we finish early, we finish early. We don't need to force it and start something new, but we'll see how things go. All right, now having or being able to use these enolate anions in different reactions, we of course have to be able to prepare them from the parent carbonyl compounds. And there's the question of which side of the equilibrium do we want to favor? The side of the parent carbonyl, the side of the enolate? We need to be able to choose the right base to get the position of equilibrium that we want. And so it's important to know the approximate pKa values of these different alpha hydrogens. And we have this generic carbonyl compound up here. The X could be a hydrogen, an alkyl group, an alkoxy group, for example. Not a chlorine atom, because acid chlorides, you don't deprotonate them. Whatever base you throw at them will not act as a base, it'll act as a nucleophile. But here, hydroxide as a base, as before, would abstract an alpha hydrogen, forming a negative charge on the alpha carbon in the enolate anion, the conjugate base of the parent carbonyl compound. And that enolate anion is resonance stabilized. It has these two contributing resonance structures. And lastly, the base that we're using is, of course, protonated, forming its conjugate acid. What is the approximate pKa of water? It kind of depends on the textbook that you're using. 16 sounds good. I think 14 is really the one, but all the organic textbooks say 16. I think there was an error somewhere along the way, and now we're sticking with 16, so we're doing that. All right, so how does the X substituent here affect the acidity of our alpha hydrogens? If we're looking at an aldehyde, if X is a hydrogen, then the pKa is in the neighborhood of 16. And so what would the corresponding enolate anion look like? Here's our minor resonance contributor. And then in our major resonance contributor, the negative charge is on oxygen rather than carbon. And I was going to ask, in terms of acidity, what other species can we compare an aldehyde to? But we kind of already spelled it out. In terms of acidity, in terms of the acidity of the alpha hydrogens of an aldehyde, clearly it's just about as acidic as water. What else has a similar pKa? Alcohols, exactly. So that allows us to just fit this into the bigger picture to see how aldehydes compare to other species in terms of acidity. Similar to water and alcohols. All right, now what if our R group here is an alkyl group, such as a methyl group? Then we're looking at the acidity of the alpha hydrogens of a ketone, and these seem to be a little bit less acidic. A little bit means, multiple orders of magnitude actually, but the numbers look fairly similar at least. So here's our enolate of the ketone. This is what that would look like. These are our two contributing resonance structures, minor and major. I can't think of a species off the top of my head that has a pKa in the neighborhood of 20 aside from a ketone. So there's that. Moving on, last scenario here. What if this X substituent is an alkoxy group, like a methoxy group? Then we'd be looking at an ester. And it turns out the esters alpha hydrogens are quite a bit less acidic with a pKa in the neighborhood of 25. And I'll go ahead and sketch the enolate anion formed from methyl propanoate real quick. And then I just want to discuss what causes the difference in acidity of these different types of alpha hydrogens. Before we do that, what else has a pKa in the neighborhood of 25? Alkynes, exactly. Terminal alkynes or 1-alkynes that have that proton bonded to the sp hybridized carbon atom. So again, that gives us some context. Now, looking at the difference in acidity, we know that a weaker acid has a less stable conjugate base. A stronger acid has a more stable conjugate base, which means that the enolate formed from the aldehyde among the three shown here is the most stable one, and the enolate formed from the ester is the least stable one. So there must be some structural feature that, destabilizes the enolate anions of the ketone and the ester compared to the aldehyde. And what is the only difference between these structures? It's X, right? So how could this methyl group compared to this hydrogen affect the stability of the enolate anion? What does the methyl group do? It's a weakly electron donating group. And what do electron donating groups do to anions when it comes to stability? They destabilize them. How do we stabilize anions? Like, what types of substituents might stabilize anions? Electron withdrawing groups, right? We stabilize anions through electron withdrawing groups, for example, through the inductive effect. Well, we're doing the opposite here. An electron donating group will destabilize an anion. Not necessarily strongly in this case, but it is noticeable in the pKa of the ketone. Less stable conjugate base, weaker acid. So what makes the enolate anion of the ester, again, less stable than that of the ketone and that of the aldehyde? We now know that electron donating groups destabilize anions, including enolate anions. So what does this methoxy group do electronically to destabilize the enolate anion? We know, of course, that this negative charge is delocalized. We can push that into the carbonyl group to generate our second resonance contributor, but this is not the only electron donating group or atom. We know that our oxygen here in our methoxy group is also electron donating through resonance. So there's a bit of a competition going on between electrons being donated from here versus from here. So this electron donating effect of our methoxy group, specifically this oxygen, destabilizes this enolate anion compared to that formed from the ketone or that formed from the aldehyde. Less stable enolate anion means our parent carbonyl compound, our original acid, must be less acidic. Okay, so just roughly our pKa's here are somewhere between 15 and 25 or so. When we add a second carbonyl group, specifically in a beta dicarbonyl compound, we see acidity increase quite significantly and pKa values are lowered quite significantly. The most acidic alpha hydrogens here are those shared by both of our carbonyl groups. And I hope you can kind of already visualize why that is. If we take our beta diketone, for example, there's one of our two alpha hydrogens, one of our two most acidic alpha hydrogens. Abstraction of this gives, of course, our conjugate base, gives the enolate anion. But this time we have two carbonyl groups as opposed to one. That'll stabilize our negative charge through resonance. So we can push our negative charge to the left into that carbonyl group. And we can push it all the way over to the right into the second carbonyl. And so not only does that second carbonyl group give us access to a third resonance contributor, that alone would help, But also that third resonance contributor has the negative charge on oxygen. So we have more resonance contributors and more resonance contributors overall that have the charge on the more electronegative atom, which stabilizes it better. And if we look at the trend in acidity from the beta diketone to this beta keto ester to this malonic ester, we can see with an increasing number of esters, acidity decreases, pKa increases slightly, which again means esters don't stabilize negative charge in the enolate as well as ketones or as aldehydes do. So we've seen that before, which means our beta diketone is the most acidic species here. This malonic ester is the least acidic one, but given that we're looking at hydrogens bonded to carbons, we're looking at CH acidity, that's still pretty acidic for a hydrogen bonded to a carbon atom. That's more acidic than water. All right. Now let's get into the specifics of the reactions of these enolate anions, starting with, I don't know if I want to say it's the most important reaction of enolate anions, but it's certainly one of the most important reactions of enolate anions, the so-called aldol reaction. Now, I'm not entirely sure where the name comes from, but it sounds to me like it's a merging of aldehyde and alcohol, the aldol reaction. It actually says it's the most important reaction. I'm not so sure. It's fairly important. We've technically already looked at it with some R groups and some X's, and so now we'll make it a bit more specific. The aldol reaction is a self-condensation of aldehydes and ketones. And so I'm showing you two examples here because I kind of want to go over, before we get into the mechanism itself, how can we go about predicting the products of this reaction without even knowing how it works? Because as you can imagine, on an exam, you're predicting products for different reactions. How do you typically go about that? Do you just know this reaction does that, and you draw the product and you're done? Or do you think about the process and about the entire mechanism? Because the first option, that's the way to go about it. You need to know what a reaction does overall, like what is the net effect, what to connect, what to disconnect, what groups to add, what groups to delete. Knowing the mechanism is helpful, but you shouldn't have to draw the whole thing to arrive at your correct product. All right, so we have two equivalents of a ketone here, two equivalents of acetone. And what will happen is that we will connect the alpha position of one of our ketone equivalents to the carbonyl carbon of the other. Initially, there will be an addition to form this beta hydroxyketone, and if heat is applied, dehydration readily occurs. And so what happens overall? We form a double bond between the alpha position of one of our ketone equivalents and the carbonyl carbon of the other. Just connect this to that, make a double bond, that's your product. Fairly easy. You don't have to use ketones, you can use aldehydes. I'm using ethanol or acetaldehyde in the second example, two equivalents of that. First, in the addition, we make a beta hydroxycarbonyl, a beta hydroxyaldehyde, connecting the alpha position of one aldehyde to the carbonyl carbon of the other. So this is an aldol addition product, the addition product of the aldol reaction, a beta hydroxycarbonyl. And again, if heat is applied, dehydration will occur, water will be eliminated. That is what we call the aldol condensation product. Condensation, more strictly speaking, meaning the elimination of water. More broadly, some people would say that it's the elimination of a small molecule that can include things like alcohols. Not everyone agrees on that. And your double bond does show easy isomerism, the more stable isomer. So the E isomer in this case is typically the preferred product. All right. Now for the mechanism of this one, whenever we tackle a new reaction, we take we'll do a bit of an overview and then we'll get into how this actually works. And we've actually looked at a good part of it, but again, in more of a general context. So let's specify and look at this aldol condensation of acetaldehyde, an aldehyde that has alpha hydrogens, and the pKa of these we said is approximately 16. We're using hydroxide as our base, sodium hydroxide, and so that'll abstract an alpha hydrogen. And I'm not going to push these CH bond electrons onto the alpha carbon because I don't want to draw the minor resonance contributor. I want to arrive at the major contributor. So I'm going to push my electrons all the way over and into the carbonyl group to again arrive at that major resonance contributor with a negative charge on oxygen, while remembering that the charge is delocalized, is shared by oxygen and carbon, and the enolate anion is a carbon nucleophile. So there's our nucleophile. There's our electron donor, and protonation of hydroxide, of course, gives water. What is the electrophile? Acetaldehyde itself. That's an electrophile. The carbonyl carbon is the electrophilic site. Now, before we get into the actual aldol reaction, the addition of the enolate to the aldehyde, let's first look at this, again, this acid-base reaction, this proton transfer that happens first. We're establishing an equilibrium between the aldehyde and its conjugate base, its enolate anion. What is the position of equilibrium? Which side does the equilibrium lie to? Take into account the pKa of your conjugate acid. Here's the pKa of your acid. Consider the pKa of the conjugate acid. Which side does the equilibrium lie to? It's a trick question. Neither? Because the pKa's of the acid and conjugate acid are the same, 16 and 16. So what's the equilibrium constant? 10 to the power of 0, which is 1, which means neither side is favored. Now, the pKa's won't be exactly identical, so one side will be favored slightly, but still, there's a good equilibrium. There's a good mixture of the parent carbonyl compound and its enolate. It's about a 50-50 mixture, not exactly, but close enough. If we're using sodium hydroxide sort of in an equimolar amount, a 1-to-1 ratio. So that, helps us out. That tells us that there are aldehyde molecules and there are enolate anions. We have both of these present at the same time. So one of our enolate anions acting as a carbon nucleophile will add to an aldehyde molecule by attacking the respective carbonyl carbon. So this right here is where our addition first happens. We're adding the enolate anion to an aldehyde. The enolate, again, as a carbon nucleophile from its alpha carbon, attacks the carbonyl carbon of the aldehyde. So we're adding a strong nucleophile to the aldehyde to give a tetrahedral intermediate. The nucleophile is simply something a little bit more complex. It's not as simple as hydroxide or an organometallic reagent. There's a little bit more going on structurally. There is no leaving group in our tetrahedral intermediate, so there is nothing to be eliminated. But our reaction mixture is an aqueous one, sodium hydroxide and water, and so our tetrahedral intermediate can certainly be protonated by a water molecule. Even if just in equilibrium, everything so far has been reversible. And protonation of the tetrahedral intermediate is giving this beta hydroxy carbonyl compound the product of the aldol addition. So here specifically, we obtain this beta hydroxy aldehyde which again is the aldol addition product. The beta hydroxyaldehyde is the product of the aldol addition. So all we've done is we've added a nucleophile, which happened to be an enolate anion, to the aldehyde. Now, dehydration for many of these beta hydroxycarbonyls occurs when heat is applied. When heat is applied, that's when dehydration occurs. Again, not all substrates require heat, but many, if not most of them do. So the question is, how exactly does this elimination work? And sometimes to get ideas for exams or just practice materials, anything really, I like to use Google image search because all you have to do is type in what you're looking for and there's like a million examples to choose from. But it doesn't always show you the right thing when you're looking at a mechanism. So you want to keep that in mind. There are some nonsensical drawings that are kind of advertised as this is it, this is how it works, and it's not. So be careful. All right, so when heat is applied, dehydration occurs. How does this dehydration occur? We do want to eliminate water by getting rid of this hydrogen atom and getting rid of this hydroxyl group. These effectively make up the water molecule that is being eliminated, but again, how is that eliminated? Reaction conditions are still basic. So what we have is hydroxide and water. What we don't have is hydronium, right? If you dissolve sodium hydroxide in water, there's not a lot of hydronium ions present. You'd need an acid for that. And so we still have our carbonyl group. And so our alpha hydrogen is at least as acidic as it was in the starting material. The pKa is 16 or potentially below that. So I've drawn one curved arrow that is part of this mechanistic step, but clearly it can't be the only one. It's doing just this, forming just this OH bond. We would overfill this hydrogen's valence shell. It can't hold 4 valence electrons. So we will break that CH bond. The question is, which way does it go? Does it go to the left into the carbonyl group, or does it go to the right and we eliminate hydroxide? Think about those possibilities and think about if there's one where kind of your alarm bells go off for a reason. Should we push our electrons to the left, or should we push them to the right? Who's for the right? The left. Right? Your intuition is a little off. I understand kind of the desire to just push electrons to the right, kick out hydroxide, make our conjugated system. That's all great, but what kind of a mechanism is that? If our substrate wasn't this, if you think just generally, when you talked about substitution and elimination in Orgo 1, what kind of a mechanism would that be? Grabbing a hydrogen, making a pi bond, eliminating a leaving group all at the same time. That's an E2 mechanism. What type of leaving group do we need for an E2 mechanism? A good one that is not particularly basic. And what is the leaving group here? A base. So that won't work too well. This E2 mechanism is not what takes place. But again, we do have this moderately acidic alpha hydrogen, so that can certainly be abstracted and will be abstracted to form yet another enolate anion. We abstract an alpha hydrogen and form another enolate anion and water. And it is this enolate anion intermediate that subsequently expels hydroxide like so. So the elimination, the dehydration, is a two-step process. It's not an E2 mechanism because the leaving group here is not a good one. First, we form an enolate anion, and that enolate anion then expels hydroxide from its beta position to give the final aldol condensation product, this alpha beta unsaturated aldehyde in this case. So there's a double bond. I'm having the hardest time with the beta. There is a double bond between the alpha and beta carbons of the aldehyde in this alpha beta unsaturated aldehyde product, the product of the aldol condensation. And now you might think, well, we've still eliminated hydroxide, which is still a bad leaving group. And that is true. But the pathway through the enolate anion is the one that occurs because, well, the enolate can readily form. We have that moderately acidic alpha hydrogen. And once hydroxide is eliminated, there is no way back. This elimination is irreversible. That's the only irreversible step here. So once that happens, again, there's no way back. We're done. Now, we don't understand most likely at this point in time why this last step is irreversible, and we're not going to discuss it today, but we'll pick this up again in a different context. Are any of you familiar with the concept of hard and soft acids and bases? Not really. Not a problem. We're not going to cover that in detail either, but again, we'll pick it up on a different day. Different context, different reaction, but we'll ultimately explain why this step is irreversible. So that may help. All right. Now, both of the examples that we've looked at here have been self-condensations. We've reacted two equivalents of acetone or two equivalents of acetaldehyde. That was a self-condensation in each case. But what if we combine two different carbonyl components, two different aldehydes and or ketones? What if both of them have alpha hydrogens, which is the case in this first scenario at the top? We have acetone, which has two equivalent alpha positions. And I'll just sketch the enolate anions that can form on the right side. So there's the one and only enolate that can form from acetone. And then we have butanone, which has two different alpha positions. There is this methyl group, the less substituted side, and there is this methylene group on the more substituted side. And so while one of the respective enolates is certainly more stable than the other, that doesn't mean the more stable one forms exclusively. Both of the enolate anions of butanone form to a certain extent. Sodium hydroxide is the base used here, so there will be an equilibrium between the ketones and their respective enolate anions, and that equilibrium will actually lie to the side of the ketone. So does this look like there will be an exclusive, a single major product here? Is there going to be one particular enolate anion reacting with one particular carbonyl compound to give one major product? Probably not, because we have these three different enolate anions, and they can react with two different ketones. We have three possible enolate anions, and they each can react with two different ketones. And heat is indicated here, which means we're taking this all the way through to the end. We're including a dehydration. So we're looking for the alpha beta unsaturated carbonyl compound. There certainly will be a product mixture. I think we would expect 6 different products, 6 different aldol condensation products, not even considering the EZ isomer, not isomerization, the EZ isomerism that is possible for some of those double bonds. So the bottom line here is that this is probably not a good way to approach this reaction. If you wanted to make a specific product from these two starting materials, this approach is not the one. There may be a better way to go about it if you desire one particular target molecule, but this isn't the one. The one that will work, we'll talk about probably next Monday. But what if one of your reactants doesn't have any alpha hydrogens? Well, then it cannot form an enolate, and then it can only act as the electrophile, not as the nucleophile. And that's the case in this next example. We have propanol, which does have 2 alpha hydrogens, and so it can be deprotonated by our base hydroxide. We're doing this under basic conditions, aqueous sodium hydroxide solution. So here's the enolate anion formed from propanol. Formaldehyde, on the other hand, there are no alpha hydrogens, there is no enolate to form. So the enolate formed from propanol will selectively attack formaldehyde for 2 reasons. Number 1, it doesn't have any alpha hydrogens, so it could not possibly be the nucleophile. It has to be the electrophile. Number 2, there are no alkyl groups attached to this carbonyl carbon. So there are no electron donating groups. Formaldehyde is therefore much more electrophilic. It's more electron deficient. So we have this crossed aldol reaction here. We're using different carbonyl compounds, and this time we should be able to generate a single major product. So first, the enolate anion formed from propanol attacks formaldehyde, forming a tetrahedral intermediate. The hydroxyl oxygen will initially have a negative formal charge. I've already attached the proton. So there's our aldol addition product. I don't want to draw a complete mechanism here. The aldol addition product, or beta hydroxyaldehyde. And once heat is applied, dehydration occurs between these alpha and beta carbons that are labeled, giving an alpha beta unsaturated aldehyde product. This is the product of the aldol condensation. Again, there is one major product here in this crossed aldol reaction because one of our reactants is more electrophilic than the other, and it lacks alpha hydrogen, so it cannot form an enolate itself. And we'll add one more example here. One more example of a crossed aldol reaction. This one's a very nice one for a lab experiment. Are you all taking lab this summer? Most of you at least, probably. I don't know if you're doing any aldol reactions. If you're not, you should totally add that because this one in particular is super easy. You just combine all the things, you let it stir, you wait an hour or 2, and everything just precipitates. It's very nice. So we're reacting acetone with a benzaldehyde. Looking at benzaldehyde, one of the alpha carbon, well, there's only one alpha carbon. It's not sp3 hybridized, but sp2 hybridized, and it doesn't have any alpha hydrogens either. So acetone, on the other hand, does have 2 alpha carbons. I'll highlight one of them because we'll deprotonate one of them with our base, which here is potassium hydroxide. And so reaction of acetone with potassium hydroxide creates an equilibrium between the ketone and its conjugate base, the enolate anion, keeping in mind that this is a carbon nucleophile, even if we show the charge on oxygen in the major resonance contributor. Okay, so there's our nucleophile, the enolate anion. Benzaldehyde will be our electrophile. Why will benzaldehyde be our electrophile? 2 reasons. Number 1, benzaldehyde lacks alpha hydrogens, so it's not like it could form a nucleophile. It's not like it could form an enolate anion. And number 2, an aldehyde is more electrophilic than a ketone. An aldehyde is more electrophilic than a ketone because it has fewer electron donating groups attached to the carbonyl. have you talked about, in the context of aldehydes and ketones reacting with oxygen nucleophiles, have you looked at the formation of carbonyl hydrates and sort of the position of equilibrium dependent on, do you have an aldehyde, do you have a ketone, is it formaldehyde? The dependence of the position of equilibrium between the carbonyl compound and its hydrate on the R groups attached to the carbonyl. I see at least someone nodding. The rest of you probably forgot. So ultimately, that position of equilibrium depends on how electron deficient this carbon is. You get more hydrate if that carbon is more electron deficient. And when is the carbon more electron deficient? If you have strong electron withdrawing groups attached, or if you have fewer R groups attached. Formaldehyde forms largely hydrate. The ratio of hydrate to aldehyde is like 40:1 or something. And a ketone, the equilibrium, well, there's basically almost no hydrate. So there's that. Okay, all right, so imagine your enolate anion forms here, attack your carbonyl carbon of the aldehyde, push your pi electrons up, forming a tetrahedral intermediate, giving a negative charge on the oxygen atom that used to be part of your electrophile, and then protonation of that same oxygen gives this aldol addition product, this beta hydroxycarbonyl. And you can see I've abbreviated the benzene ring, the phenyl group, just to save some space. And this beta hydroxy ketone will now dehydrate to give the alpha beta unsaturated carbonyl compound, the alpha beta unsaturated ketone. Water is eliminated to give this aldol condensation product. And typically we apply heat to make this happen, but I put in parentheses because this particular example won't need heat. This dehydration occurs readily at room temperature. Can you think of a reason why that might be? This is a benzene ring, right? So why might this dehydration occur so readily at room temperature? It's like it's really wanting to. Like it's eager to dehydrate. Why is it eager to dehydrate? Because you're not making a simple conjugated system between a carbonyl group and a carbon-carbon double bond. That itself is pretty good, but you're literally connecting the carbonyl group and the phenyl group through conjugation with an intervening double bond. So you're making a much larger conjugated system. You're helping much more when it comes to stability. That's why the dehydration occurs much more readily. Now looking at acetone again, acetone has 2 alpha carbons, both of which have multiple alpha hydrogens. So it turns out acetone can react twice, once on each alpha carbon atom. It can react twice with benzaldehyde. So if you combine acetone and benzaldehyde in a 1:2 ratio, so we're going to do that, 1 equivalent of acetone, 2 alpha positions, and 2 equivalents of benzaldehyde. Otherwise, same conditions, potassium hydroxide and methanol. Both sides, both of the alpha positions of acetone will react with benzaldehyde, and our product will be this. Acetone can react twice with benzaldehyde, and it can react at both of the alpha positions. So there's 2 aldol condensations taking place. And the product that we see here, very nice yellow crystals, this is fairly straightforward to make. It's used, for example, as a palladium catalyst. So there are commercially available palladium catalysts where this molecule is a ligand on palladium. Okay, so we've looked at 2 different types of crossed aldol reactions where we use 2 different carbonyl compounds, one where both components have alpha hydrogens, and we saw that's a cluster mess. Let me call it that. not a good idea. It'll just give a mixture of products, and that's typically not what we want. We want one major product, the one that we aim for, and not, a random mixture of 6, and hopefully ours is a major component. That's not good enough. We can use one component that lacks alpha hydrogens to cleanly give one major product. But what if you don't want to use a component that lacks alpha hydrogens? What if you have to use these two? Like, what if you absolutely have to use these two and make one of the 6 possible products? Then you'll have to try a different approach. And that approach is using a much stronger base, using LDA. We won't get into that today. We'll pick that up again at the end of this chapter. Like I said, probably next Monday. Okay, so that was most of the aldol reaction. There is still the intramolecular aldol reaction. Probably not something we'll cover today, but what we will cover today is a reaction that technically has a different name, the Henry reaction, but it really is just a variant of this aldol reaction. The Henry reaction, a variant of the aldol reaction, is also referred to as the nitroaldol reaction. Uses one carbonyl component that can, let me leave it at that. It uses one carbonyl component, it uses one aldehyde or ketone, and that aldehyde or ketone will serve as the electrophile. And in addition to that, we're using not a second carbonyl component, but a nitroalkane. Commonly nitromethane, also used in racing fuel. My husband's been watching on YouTube, like a drag racing. So methanol fuel with nitromethane added or something. I don't know. Where was I going with this? So you can use nitromethane, but you can also use other nitroalkanes, nitroethane, nitropropane, stuff like that. All right, and so your nitroalkane will ultimately give the nucleophile. How that works, we'll look at shortly. And if we take this reaction through to the end, we're also going to end up with a double bond with a nitroalkene product. This one here is nitrostyrene. Also a common reaction done in organic labs. Probably not in yours. This one's a little bit finicky. If you don't get the pH right during workup, you get almost no product. And sometimes the textbooks or the lab manuals, kind of skip that part. So that can be an issue. All right. Now looking at this, you might wonder, like, how is that kind of parallel to an aldol reaction? And we will see how when we take a closer look at the structure of the nitroalkane. So I've started with the hydroxide ion. I'll go ahead and draw nitromethane. And when we draw that nitro group, we have a positive formal charge on nitrogen, and one of our 2 oxygens has a negative charge. So if you look at that nitro group in nitromethane, if you squint a little bit, doesn't that look kind of like an aldehyde or ketone, kind of like a carbonyl group? Like I said, you do have to squint. If we pretend this is a carbon atom, I mean, you have something that looks kind of like a carbonyl group that could accept electrons. And so that's how this is going to work. The nitroalkane is actually quite a bit more acidic than an aldehyde or ketone with a pKa in the neighborhood of 10. What else do we know that has a pKa of 10? Phenol has a pKa of 10, 9.95, just about the same. So again, for context, that's how that fits into the bigger picture. So we have a nitro group that'll kind of function like a carbonyl group. And on the neighboring carbon, on the alpha carbon, there are several hydrogens attached that are quite acidic. And so one of these can easily be abstracted by our base. In this case, hydroxide. Hydroxide is definitely strong enough. Okay, so first I'm just pushing my CH bond electrons onto the carbon atom next to the nitro group. So I'll create a negative formal charge. I'll create a lone pair. But that charge, like it would be in an enolate anion, is resonance stabilized. We can push that charge, bless you, into the nitro group, making a carbon-nitrogen double bond. And we'll end up with negative charges on both oxygens in this nitro group. Don't forget the positive on nitrogen. So deprotonation of this nitroalkane of nitromethane gives the conjugate base a so-called nitronate anion. A resonance stabilized nitronate anion is what forms in the deprotonation of the nitroalkane, here nitromethane. And given that we're looking at yet another acid-base equilibrium, which side does this equilibrium lie to? What is the side of the weaker acid? pKa of the conjugate acid is 16, so the conjugate acid is weaker than the acid. The equilibrium lies to the right side, with an equilibrium constant of 10 to the power of 6, which is 1,000,000. So there's a ratio of products to reactants of 1,000,000 to 1. There isn't much reactant left. This deprotonation is basically quantitative. It's complete. Okay, and so once our nitronate anion has formed, and I won't walk through the entire mechanism because really it's entirely parallel to the mechanism of the aldol reaction. There's our nitronate anion. Remember, the negative charge, is delocalized, is shared by carbon and oxygen. Carbon is a better electron donor, and nitronate anion, just like an enolate anion, is a carbon nucleophile. And as a carbon nucleophile, the nitronate anion, just like an enolate would, will attack the carbonyl carbon of your aldehyde in this case. Your nitronate anion acting as a carbon nucleophile will attack your aldehyde, will attack benzaldehyde, forming a tetrahedral intermediate. And that intermediate is subsequently protonated and dehydrated to give the nitroalkene product. And that'll be the end of that. What I recommend you do is try to draw that mechanism. Just follow the steps of the aldol mechanism, and you can do them side by side. What you can try to do is draw two mechanisms side by side, kind of one step at a time. On one side, react benzaldehyde with nitromethane, and on the other side, react benzaldehyde perhaps with acetaldehyde as kind of your fill-in for nitromethane, so that you can see that parallel. Okay, so why are we covering this reaction? What's the significance of having that nitro group? Why do we want to be able to make nitroalkenes, or perhaps the beta nitroalcohol intermediate that we would form? You know, why is it important to be able to do that? Well, one of the reasons is that the beta nitroalcohol intermediate, which we can reduce to beta amino alcohol intermediates, the beta amino alcohol motif is important in a number of applications, and that includes pharmaceuticals, that includes drug molecules. And one of them is shown here in this example. This is propranolol, a beta blocker. And we can make it in a synthesis that's relatively short that involves a Henry reaction. So we'll see, we probably have enough time to go over this. We're going to look at the synthesis of propranolol from all of these starting materials. And what I like to do to get started here is to kind of just see how the atoms in the starting material fit into the target molecule. I'm literally looking for matching shapes. It's kind of like a puzzle. And then we look into how we make the individual connections. What reactions do we know? What reactions make sense? And so clearly we have this whole naphthalene ring system over here, bridging through an oxygen to these two carbons, which must be those two carbon atoms in the target molecule. You have acetone, so you have this fork, which you find in the target molecule over here. And then you have nitromethane, which contains one carbon and a nitrogen, which we find in the target molecule right here. So that's how the pieces go together. Now, we don't know of any way to connect the carbonyl carbon of acetone somehow to the nitrogen and nitromethane. So that's probably not what we tackle first. But we know that the nitroalkane can form a nitronate anion and react with an aldehyde. And we are making a connection between this carbon and that carbon. So maybe that's how we will get started. And I will abbreviate all of this as an R group because I'm lazy. So we'll react to this aldehyde with nitromethane in the presence of base. And I'm just generically going with potassium hydroxide and methanol. You have creative freedom on paper: sodium hydroxide, water, sodium methoxide, methanol, sodium ethoxide, ethanol, whatever. Potassium hydroxide, methanol is what I'm going with, just because I know this to work well in some of these reactions. So nitromethane and potassium hydroxide will react to give a nitronate anion. If this was an exam problem, you wouldn't draw this, but I kind of want to illustrate part of the process here. That would give this nitronate anion, that would be the nucleophile attacking our aldehyde. And we're actually going to do only an addition. We're going to add our nitronate anion to the aldehyde, and then we'll protonate. And that gives this beta nitro alcohol. The addition reaction gives this beta nitro alcohol. We don't want to dehydrate in this context. Could take this further, potentially by applying heat, but we don't want to. We don't want to make a double bond here. We want this beta nitro alcohol. We're going to need it to make our carbon-nitrogen bond in the end. And perhaps we recall how to make a carbon-nitrogen bond in a reaction that involves an aldehyde or ketone and an amine, but not a nitro group. And so what we need to do is turn that nitro group into an amino group, which requires a reduction. So we want to turn our beta nitro alcohol into a beta amino alcohol using a reduction. So what reduction works to reduce a nitro group? A simple catalytic reaction, or reduction rather, with hydrogen gas and a transition metal catalyst. I'm going with nickel here, but you can use palladium or platinum. Catalytic reduction of nitro groups is easy enough. And this isn't the only way to reduce a nitro group, but this is a pretty straightforward one. So that's what we'll go with. Reduction of the beta nitro alcohol gives a beta amino alcohol. And then we can react the amine with acetone. But reacting a primary amine with a ketone doesn't make a CN single bond, right? It makes a CN double bond. It makes an imine. Is there another reagent that you're aware of that we could throw in here that would fix that? And you may not have covered that. Can you think of anything? I mean, ultimately making the imine, the CN double bond between this carbon and that nitrogen, or this carbon and that nitrogen, what we would have to do afterwards is we would have to reduce, right? We can do this in one pot. by adding a reducing agent, and that reducing agent is sodium cyanoborohydride, NaBH3CN. So it's like sodium borohydride, but one hydrogen is replaced with a cyano group, and that reduces its activity, its reactivity. It's a bit weaker of a reducing agent, which means that it won't reduce the ketone, but it'll reduce the iminium ion intermediate that forms, that has the CN double bond with a positive charge on the N. I'm not sure I want to draw it out right now because we're just about out of time. Maybe we'll pick that up again next time. We'll illustrate how exactly this works. It's really fairly straightforward. And we'll leave it at that for today. I'll see you next time.